Hello everyone, today we'll be doing this physics question and finding the final temperature Tf of a sphere of radius r, density ρ, specific heat capacity C. It has the original temperature of T0 and we'll be finding the final temperature Tf at the time T. So the sphere is going to be in outer space, meaning that there's a few assumptions we can make. First, we can say that the temperature of your outer space is going to be very close to 0 kelvins. So there's not going to be much heat that is transferred from the outer space to the sphere. So it's just sphere to outer space. That's the first assumption we can make. Second assumption is that in outer space, it's almost a vacuum, meaning that there are very little particles here. So when we're talking about conduction or convection, all two of these mediums of heat transfer, they need they need the movement of particles, which we don't have because there are going to be very little particles in outer space where it's vacuum. So we can neglect both of them, meaning that the medium of heat transfer here we're going to consider is only going to be radiation. Okay, so let's start with some equations. First of all, the equation for radiation is going to be that the power is surface area epsilon sigma T to the power of 4. So this is the Stefan-Boltzmann Law. Power is simply the change in energy per unit time. A is just the surface area. E is the emissivity, which is simply a ratio of the radiant heat, how much heat this object radiates of object over the radiant heat of ideal black body, which is the object that radiates 100% of the heat. It's the perfect emitter. Right, sigma is just the Stefan-Boltzmann constant, and temperature is just temperature in kelvins. So this is actually the full equation, right? And of course, because this energy is decreasing, there needs to be a minus sign here. So this decrease in energy causes a decrease in temperature, and if we look at the variables that's given, your specific heat capacity C, it's quite obvious that the formula we need to use is Q is mc delta T, right? Or more specifically, this is a change in Q, right? So we can basically write that dQ is going to be mc dt for very small changes in thermal energy and temperature. We can also change the E on top to Q because this is going to be the change in energy, right, per time. It's just the same notation. So right now we have two equations and we can relate them together. So you already know that we're going to need some integration here because this temperature decreases over time, meaning that the power decreases over time, right? So integration is needed to solve this. So let's first change equation 1. Equation 1, if we multiply by dt on both sides, we get dq is negative a epsilon sigma t for dt. So now we can equate both these equations. Right. So but we can simplify this. We can do a little better. The mass is nothing more than the density. Then the density multiplied by the volume, which is going to be the density, and this is a sphere, so the volume is given by 4/3 pi r cubed, and your surface area is, because it's a sphere, it's 4 pi r squared. So we can further simplify this. Let's see. Get 4 over 3 rho pi r cubed c dt is negative 4 pi r squared epsilon sigma t to the power 4 dt. So now we want to bring this t and match it with this dt so we can integrate. But before that, we're gonna have to do some cancellations, right? We can divide, in fact, both sides by 4, multiply them by 3, so we'll get 3, cancel out the pi, 3 rho r cubed c dt is going to be equal to, so I divide by 4 and multiply by 3, sorry, so this is actually 1. Right, if I divide by 4, multiply by 3, I'll get minus r squared. I can cancel that too, so not r cubed, it's just r. Right, so we negative epsilon, so negative 3 epsilon sigma t to the power 4 dt. So let's move this t to the power 4 over. Get rho r c t to the power of negative 4 dt is negative 3 epsilon sigma dt. So finally we can integrate. We'll be integrating this from your initial temperature T0 to final temperature Tf. So this will be T0 to Tf rho rc t negative 4 dt, and we'll be integrating this. So at T0 the time will be 0, at Tf the time will be certain t. Right? After time t has elapsed, it will be at Tf. So we can finally integrate. This is going to be t to the power negative 3 over negative 3. Evaluated T0 to Tf. It's going to be negative 3 epsilon sigma, and this is simply t from 0 to t. We can get rid of the negative sign also. Just do some simplifications. Yep, so now we want to isolate this equation and for Tf. Right, so we can simply move everything to one side. And this is going to be the final equation that we get. So this allows us to find the final temperature of a sphere which radiates heat in terms of all these parameters. So after integration, we finally found this, and let's just use an example. For example, if we consider a copper sphere, right, where rho is going to be 8941 kilograms per meters cubed. C is going to be for copper is 385. All these constants say that E epsilon 0.6, and TO, the origin temperature is going to be 5,000 kelvins, and your radius is going to be, let's say, 10 meters, and finally the time, we'll let it rest for maybe an hour, which is going to be 3,600 seconds. Right, and of course my Stefan-Boltzmann constant is given by 5.67, is 10 to the power of -8. Right, so without further ado, let's find the final temperature of this copper sphere. It's just going to be the cube root of 1 over 9 epsilon, which is 0.6, sigma, which is 5.67 to the power of -8, time 3600 over rho, which is 8941, radius could be 10 meters, and C is going to be 385 plus 1 over the original temperature, which is 5,000, and I'm going to cube that. So let's find this expression with my calculator really quick. 6, 8 is 3600, and the calculator gives me a value of 2923 kelvins, which is 2920 kelvins for 3SF. So you can see that after 1 hour, your temperature of this copper sphere goes from 5,000 kelvins to 2920 kelvins due to radiation. So we solved this problem and found a very beautiful formula to describe it. So that's it for this video. Leave a like if you enjoyed.